Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is resistors in series. Our objective is to take a look at series or inline configurations of resistors. Additionally, we'll discuss the influence of shorts and opens inside series circuits. This lecture operates the presumption the viewer has more than a passing familiarity of the 4-band resistor color code. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. A resistor is a component that resists, controls, or otherwise opposes the movement of electrical charges. Simple resistors are two-terminal components with fixed standard values and come in various power ratings. The polarity or orientation of a resistor doesn't matter. I mean, you can flip it around and connect it however you want, such that current goes in either direction. This is not always the case for all components. You'll find other components, such as diodes, purposely block current in one direction and allow it to flow in the other. Other components, such as certain types of capacitors, can be irreparably damaged if you hook them up incorrectly. The point is, pay attention to the markings on the outside of a component, obey manufacturer's recommendations, and hook it up like you're supposed to. A circuit is a complete path or a closed loop. The loop could be a single, circular, rectangular, triangular, or any other shape forming a complete loop, or composed of many different pathways that at least one of which allows a passage from one terminal or voltage source to the other. Without at least a single closed loop, there is no circuit and there is no way conventional current can flow from the positive terminal to the negative terminal. A closed circuit requires a closed path for current to flow. Circuits composed of multiple resistors can assume numerous different configurations, perhaps the simplest being a series or inline configuration. A series arrangement means there is one path and one path only. Here's an example of a series circuit consisting of resistor 1 having a value of 330 ohms between node A and B, and resistor 2 having a value of 560 ohms between node B and C. It should be obvious that any current emanating from the positive terminal of the source must travel into resistor 1, out of resistor 1, into resistor 2, and out of resistor 2 to reach the negative terminal of the source. This implies that the source sees a total resistance equal to the summation of resistor 1 and resistor 2. That's it. Series resistances add up. Do you need a formula to remember this? For this series circuit consisting of a 330 ohm resistor in series with a 560 ohm resistor, the source sees a total resistance of 330 plus 560 or 890 ohms. Too easy. This implies that the source would be none the wiser if the series combination of two resistors was swapped out and a single 890 ohm resistor took their place. This easier visualization can be used in circuit analysis to simplify the analysis procedure. You'll note the shorthand for resistors in series is addition, implying a series simplification has occurred. Let's put your understanding of this simple concept to the test with this series of example problems. For each series circuit, determine the total resistance seen by the source. Express all answers using proper engineering format to the tenths place. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. For the first circuit, the source sees a total resistance of 1000 plus 680 or 1680 ohms, or more appropriately, roughly 1.7 kiloohms. The second circuit first necessitates interpretation of the 4-band resistor color code. Red, purple, brown is 27 followed by 10 or 270 ohms. Purple, green, brown is 75 followed by 10 or 750 ohms. And finally, gray, red, brown is 82 followed by 10 or 820 ohms. The source sees the summation of 270, 750, and 820 for a total of 1,840 ohms, or more appropriately, roughly 1.8 kiloohms. Finally, for our third circuit, the source sees a summation of 330, 240, 470, and 430 ohms for a total of 1,470 ohms, or more appropriately, roughly 1.5 kiloohms. Note how the total resistance of a series combination is always larger than the largest resistor. If your calculations or observations suggest otherwise, you are doing it wrong. Series resistances always add up. Here's another set of series circuit example problems, each with the intent of illustrating an important property of resistors taken in series. See if you can determine the total resistance seen by each source for each of these series circuits. Express all answers using proper engineering format to the tenths place. Be on the lookout for interesting results. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. The first three circuits are just different configurations of the same three resistors in different orders. As such, the total resistance for each of these circuits is 1,770 ohms, or more appropriately, roughly 1.8 kiloohms. This example is intended to illustrate that the order of resistors constituting a series circuit does not influence the total resistance seen by the source. Any series configuration of these same three resistors in any order always results in a total resistance of roughly 1.8 kiloohms. For our fourth circuit, the source sees a total resistance of 2,480 ohms, or more appropriately, roughly 2.5 kiloohms. This example was intended to illustrate an important time-saving feature for series circuits composed of identical resistors. The total resistance of a series combination of identical resistors is the resistance value times the number of resistors having that value. 620 plus 620 plus 620 plus 620 equals roughly 2.5 kiloohms, as does 4 times 620. Finally, for our fifth circuit, the source sees a summation of 0.5 ohms, 200 ohms, and 180 kiloohms, for a total of 180,200.5 ohms, or more appropriately, roughly 180.2 kiloohms. This example was intended to illustrate two facts. One, that the largest resistor in a series relationship, in this case the obscenely large 180 kiloohm resistor, seems to dominate the whole relationship, and two, the smallest resistor in this series relationship, in this case our minuscule 500 milliohm resistor or 0.5 ohm resistor, seems to get lost in the noise.